So this podcast is designed to give you practice using L'Hopital's rule to calculate various limits. So there are 4 questions here, and what I would suggest you do is that you write them down, try to solve them using pen and paper, and then after you've given them a good go, you can come back and look at the solutions and see if you've got them right. So I suggest you write them down and then pause and come back in a minute. Welcome back. Let's now look at the answer to the first question. So the first question has the form of a product of the square root of x multiplied by the log of x, and we're interested in the limit as x goes to 0. So this will approach 0 itself, but the logarithm of something which is approaching 0 is approaching minus infinity. So the form of our structure here is something which is going to approach 0 times infinity. So what we do is we rewrite this as a quotient of a function divided by another function, and then we're going to use L'Hopital's rule to say that the limit is going to be given by the limit of the derivative of the numerator divided by the derivative of the denominator, and this is assuming that everything is differentiable. So let's look at rewriting the function whose limit we're interested in. So we're going to write it as the logarithm of x in the numerator divided by 1 over the square root of x, and this is purely an algebraic rearrangement of this structure. You could write it as the square root of x divided by 1 over the logarithm, but that is not a very profitable thing to do, and you're welcome to explore why that doesn't work. So let's look at this. We're going to use L'Hopital's rule, so we're going to differentiate the numerator, the logarithm, and we're going to differentiate the denominator, 1 over the square root. The derivative of the logarithm gives us 1 over x, and the derivative of x to the minus a half is, well, we bring the minus a half to the front, reduce the power by 1 from minus a half to minus 3 over 2, and so we obtain this. And now, to see whether this has a good limit, what we do is we multiply the top and the bottom by x to the 3 halves. So it's just an algebraic rearrangement. X to the 3 halves times x to the minus 3 halves is going to give us 1. And 1 over x times x to the 3 halves is the square root of x. So that's the powers of x, and then here we are dividing by minus a half, and that is equivalent to multiplying by minus 2. And now this is our result here, and we're interested in the limit as x goes to 0 of this result, so it's minus 2 times 0, so we conclude that the answer here is that the limit of this product is going to vanish as x approaches 0. And with that, we can move on to the next question. So the second question asks us to look at the limit as x goes to 0 of 1 minus e to the minus x over x. Well, as x goes to 0, this is going to vanish, so it looks as though we're going to be dividing by 0, but the numerator is 1 minus e to the minus x, so as x goes to 0, we'd have 1 minus 1, so this looks like 0 over 0, and we have to think hard about what the limit is. So now what we do is we're going to use L'Hopital's rule. The numerator and the denominator structures are clearly given to us here. So we're going to differentiate the numerator, differentiate the denominator, and look at what happens as x approaches 0 for this ratio. So this is what we have. We differentiate the numerator, differentiate the denominator. The derivative of the numerator is 0, and then when we differentiate the denominator, we're going to bring a minus sign in front. Minus minus becomes plus, so we have 0 plus e to the minus x, and the derivative of the denominator is just 1. So we now look at this as x goes to 0. We're no longer dividing by 0, this is 1, and as x goes to 0, e to the minus 0 goes to e to the 0, which is 1. So we're going to have 1 over 1, which is 1. So we conclude that this limit is going to be 1. It's perhaps worth noting that there is an alternative approach to this problem here, which is we're interested in what happens to this function as x goes to 0, and e to the minus x has a Maclaurin expansion, or a Taylor expansion if you prefer, as x goes to 0. So we can expand the numerator. 1 minus e to the minus x is 1 minus, and the expansion of e to the minus x is 1 minus x plus terms of order x squared. And that's something which, if you know Taylor and Maclaurin expansions, you can easily verify. The 1's cancel, as you would expect, because this vanishes when x is 0. And we're left with an x plus terms of order x squared. And now we could divide top and bottom by x. The x would cancel here with this. We'd get a 1 plus, and instead of terms of order x squared, we'd have terms of order x, which would vanish as x goes to 0. So we would be left again with 1. So that is an alternative method for looking at this problem here. No, we could not have used it on the exercise that we solved first, because log of x does not have an expansion as x goes to 0. For that, we need to use L'Hopital's rule. So with that, we'll move on to the next question. So our third exercise is to study the limit as theta goes to 0 of sine of theta over theta. And this is a very important problem which is used, for example, in showing the derivative of the sine function. So let's consider this. As theta goes to 0, the sine of 0 vanishes. We'd have 0 over 0. So this is something which we'd naturally use L'Hopital for. And we're going to recall that the limit as theta goes to 0 of the ratio of these two functions is the limit as theta goes to 0 of the ratio of the derivatives of each of the functions. So we differentiate sine of theta, and assuming that the angles are measured in radians, that's going to give us the cosine of theta. Differentiate theta, we get 1. So the limit as theta goes to 0 is going to be cosine of 0, which is 1 over 1, so we're going to obtain 1. So we conclude that the limit as theta goes to 0 of sine of theta over theta is 1. And I will leave an exercise for you to show that if you look at the Maclaurin expansion of the sine of theta, then you will obtain exactly the same answer. So that's just looking at that in the same way that we alternatively considered the previous exercise. There is also an extremely nice and important geometric proof of this result, and you can find that if you look at the podcast on the derivative of the sine function, and that's well worth being on top of. Okay, so with that, let's move on to the final question. So the final exercise is to calculate the limit as x goes to 0 of the log of 1 minus x over x. And as x goes to 0, the denominator will vanish, but the numerator is going to approach the log of 1, which also vanishes, so this has the form of 0 over 0, and we want to use L'Hopital's rule. So what we're going to do is differentiate the numerator and differentiate the denominator and calculate the limit as x goes to 0 of that new ratio. So the derivative of the log of 1 minus x, it's going to be 1 over the argument of the log, so 1 over 1 minus x, times, because we're using the chain rule, the derivative of the argument of the logarithm, so the derivative of 1 minus x. This is going to be minus 1 multiplied by 1 over 1 minus x, so that's minus 1 over 1 minus x, and the derivative of x is just 1, so in some sense this is all over 1, but that's the same thing. So we're interested in the limit as x goes to 0 of this, and as x goes to 0 we have minus 1 over 1, so we get minus 1. So this is the limit of that function. And again, as an exercise, you can show that you obtain the same result if you use the Maclaurin or Taylor expansion of the logarithm of 1 minus x. You only need to work out the first correction to the Maclaurin expansion of log of 1 minus x to obtain this result. So we've calculated 4 problems using L'Hopital's rule. The first one is a classic problem for which there is no alternative. You cannot use Maclaurin expansions. And then the other problems, we've been able to back them up by using Maclaurin or Taylor expansions as well. And for the sine problem, there is a very nice geometric proof as well. And with that, I will stop this podcast.